So during the day I do fire protection engineering, code consulting, life safety code consulting, and then in my spare time I get into human behavior and studying that. So it's good to be in light company who also enjoy that type of thing. I tell my wife that I enjoy doing this on the weekends and she laughs at me, but I think you guys understand. So my talk today is looking at the impact of stairwell queues on egress time from a floor. I think all of us have been in some sort of evacuation from a building, whether it's a fire drill or a real fire, and we've been inside a stair that looks something like this, where it's just a huge mass of people, and you're kind of scratching your head wondering if there's an actual fire in here, am I going to get out in time? So queues are not an uncommon thing in evacuations, and they've been studied at length in empirical data, and then in modeling studies, we spend a lot of time trying to figure out how do queues form during an evacuation, how do we resolve the queues. This is from the Pathfinder User's Guide, and anyone who's ever done any egress modeling, you spend a lot of time figuring out where does the queuing occur. Perhaps the most famous picture of a stairwell queue is this one. So this is taken from a stair in the North Tower of the World Trade Center on 9/11. And you can obviously see the queuing occurring on the outer portion of the stair as the fireman comes up. So queuing is a phenomenon that occurs basically in every evacuation from a building. And as I've studied this more and more, I did some graduate work on evacuation from high-rise buildings at the University of Maryland. I did that work with Dr. Erica Kulagowski, and we studied what are the actual parameters of a queue. And really the first place that you see queuing in a modeling sense is the SFPE hydraulic model for egress. Steve Gwynn is here somewhere and had something to do with this. But essentially the hydraulic model, which most of you I'm sure are familiar with, is a set of flow rate and velocity equations. And queuing essentially occurs anytime that the maximum specific flow for an egress component is exceeded. So you have a maximum specific flow for a door or a stair, and if the actual flow rate going through that exceeds that maximum, then queuing is going to occur on the other side of, or on the incoming side of that egress component. When you have a merging flow, for example, the merging of occupant flows that occurs down the stair and occupants coming onto a stair landing, the hydraulic model says that if the sum of these two inflows is less than the maximum specific flow, then the outflow rate from this merging event will just be the sum of the inflows. And if the sum of these two inflows is more than the maximum specific flow, then queuing will occur, and the rate of that queuing is going to be the difference between the sum of those and the maximum specific flow. So that's pretty standard. That's what the hydraulic model says in the SFPE Handbook. 4 years ago, I presented at this conference and gave a talk about how there's some empirical evidence to show that actually the sum of these two incoming flows is not actually equal to the outflow, and there's some inherent inefficiency that occurs during this merging event. And we have empirical data from a set of NIST evacuation videos that shows that on average, this outflow rate is about 75% of the sum of these two inflows. So that's all well and good. And as I thought about this more, I got to thinking, as there is this apparent inefficiency in merging events that occurs on each stairwell landing, what happens in high-rise buildings where you have hundreds or maybe even thousands of these merging events that occur all throughout the building during an evacuation? And like I said, I am a code consultant during the day, and if you look at model building codes in the US and also many model building codes internationally, there is not a lot of, there's not many requirements that take into account this multiplying effect that happens as you have more and more of these egress inefficiencies during a merging event. So logically, it made sense to me that the taller or larger the building that you have, the greater the impact of this inefficiency, meaning the more of these merging events that happens, the greater the inefficiency. And then do any model building codes account for this in any egress requirements based on the number of stories or the height of the building? And at least in the US, the answer is no. There are a few related requirements. For example, the International Building Code requires one additional exit for buildings that are taller than 420 feet. The IBC is adopted in every state in the US and also in some international countries. NFPA 101 is adopted in a handful of American states and also in a number of international jurisdictions. 101 allows for actually a reduction in egress width, a reduction in the egress width factor when your stair is wider than 44 inches. But then it also does require an increase in the minimum stair width for a stair serving an occupant load of 2,000 people or more, and that's the cumulative occupant load in the stair. So really, in all of the codes that are enforced in the US, these are the only requirements for egress that's based on the height or the number of stories in the building. So that means that if I were to build a building here in Montgomery County, Maryland, I could have a building that's 2 stories or a building that's 35 stories, and the requirements for the number of exits and the requirements for the total egress width are the same in those 2 buildings. And that's true of almost every jurisdiction in the United States. So I got to thinking, why is that? Why do the model codes that we enforce not account for the height of the building in determining egress requirements? So decided to put together a very simple model using Pathfinder to determine what is the impact on the overall egress from a building when you use the number of stories as the variable. So I created a very simple geometry here in Pathfinder. This is just it's a 10,000 square foot square floor. There's 2 exits. The width of the stairs is 44 inches, which is the most common stair width here in the US. 11-foot floor-to-floor height, also very typical, and a door width of 33 inches on the stairs. All very common, very typical egress component sizes here in the US. Applied a 1 to 100 square foot occupant load factor, which is what's currently enforced for a business office space type occupancy in both the IBC and 101. And we just ran a simple model looking at simultaneous evacuation. So all occupants throughout the model are evacuating at the same time. And so what we did is we took that floor plate and we ran a simulation starting with just 2 stories of that floor plate and then ran it over and over each time, adding an additional story to the model. And we did the simulations in both the SFP and steering modes in Pathfinder, and it was a simple evacuation, so we just considered the discharge as an exterior door here at the base of each stair. So we ran that and we took a look at the results, and what we would expect, I don't think anyone would disagree, that the overall evacuation time from the building will increase with the number of stories. That's very logical. No one would expect anything different. And we saw that here in the data. So this top line here is the total building egress time. And that's this top line. So each time we added a story to the model, the total time to evacuate the building went up. We expected that. That makes sense. These other 2 lines are something that maybe is not as expected. And this middle line here is the maximum time to clear any given floor in the model. So for example, looking at this 10-story modeling simulation, this time here is the maximum time for any one floor in the model to clear the floor and all occupants enter into the exit stairwell. And then this final curve here is the average time for occupants in each of the stories to clear the floor and enter into the exit stairwell. So what is this telling us? This means that as the number of stories increases in the building, the time for any one floor to clear, all the occupants from that floor to get into the stair, is also going up, right? And I think for us here in this room, that makes sense. We've all looked at egress models and we've seen the queues that occur outside the stair door. And the bigger your model, the more queuing that occurs throughout the building. But what's crazy is that this phenomena is not really addressed in any building code that's enforced in the US, in the IBC or in NFPA 101. So again, I could have a 2-story building here in Montgomery County, Maryland, or a 35-story building. And if I had this floor plate in that building, I would only be required to have 2 exits, each with a 44-inch stair. But if you extrapolate this data out to 35 stories, you can see that the average and maximum times to clear any given floor is going to be vastly different for a 35-story building versus a 2-story building. So again, this is an SFP mode. We see very similar data in the Pathfinder steering mode. It's essentially the exact same trends. The actual times are slightly less for the steering mode, which is very consistent with what we see in the Pathfinder User's Guide and really any modeling work that I've done. But again, the same trend for both the total egress time from the building, but also the max and the mean times for occupants to clear a floor and enter into the stairwell. And again, this phenomena is something that's really not addressed in any building code in the United States. So what do we do with that? What does that mean for us? The total egress time is proportional to the number of stories, total egress time from the building, but that was expected. The mean and maximum time is also proportional to the number of stories. So the more stories, the higher your building, the longer it's going to take on average and at a maximum for occupants to clear a floor and enter into the stair. So I floated this around to my colleagues who are also code consultants and fire protection engineers, and one thing we talked about was partial evacuation. Building code, the model building codes as well as NFPA 72 do allow partial evacuation. The most typical way that that's done is by egressing or providing occupant notification on the fire floor plus 1 floor above and 1 floor below. Doing that, and let's say you're just evacuating 3 stories of a building rather than the entire building, that's obviously going to diminish the number of these merging events that's occurring and would theoretically then reduce the rate at which the slope of these lines, or which basically it would reduce the slope of this line actually, the rate at which the time is increasing per stories in the building. So that is one thing to consider. Unfortunately, there are many jurisdictions, though, that do not allow partial evacuation. Many government jurisdictions, such as the GSA, Architect of the Capitol, many of the other government jurisdictions here in DC won't allow partial evacuation in their buildings for one reason or another. There's also many existing high-rise buildings that have a fire alarm system that's not set up or programmed to do partial evacuation and would require some retrofitting or a new fire alarm system altogether in order to handle a partial evacuation strategy. I think this is obviously it's a very preliminary study, but in my opinion at least, it calls for some additional analysis to see does this trend continue as you expand it to taller buildings or more complex buildings. The geometry I chose was obviously very simple. But I would guess that if you did this with a more complex floor plate or a taller building, you'd see much of the same. Obviously, this is just it's a representation of a phenomena that we think exists, but it's representing it using a model. It would be very interesting to see if the same trends exist in actual evacuation data. I think that is, in my opinion, that's a great opportunity for us in the egress modeling community to influence building codes, which are, at least in the US, 99% of buildings that are built to prescriptive egress requirements and not done using a performance-based egress analysis. But this could be an opportunity for us in the modeling community to influence what goes into prescriptive code requirements, which are used for the vast majority of buildings built in the US. And yeah, I mean, I kind of just said this, but there are folks who are inputting code changes and debating code requirements in NFPA committees, in the ICC general meetings, things like that, that have no idea of any phenomena like this or any trends like this. So I see it as our responsibility as egress modelers to inform these people who are making codes that are enforced in buildings that we are all residing in, to make them aware of such trends and see how can we use this phenomena, use this data to impact future code changes, future code cycles. So again, this is a very preliminary study, but I think that there's a lot of additional work that could be done. And ideally someday I would love to see this expanded to the point that it can influence model building codes in the future. So I think we have a break coming up, so hopefully I'm not too late for that, but we can take some questions now before the break.
Yeah, you actually ran a few minutes ahead, so we certainly can take a few questions.
Okay.
Hi, Chris. So you have the maximum time for a single floor and the average time for floors. Is that across all floors in the building? You just take the average of them all and get that mean?
Yeah, so let me, the mean time is, let's say for the 5-story building, the mean time was the average across those 5 floors. And then the maximum would just be the maximum of all 5.
Did you look at the difference in evacuation time for like the 1st and 2nd story as you add heights? Do you see any effect from that yet?
Yeah, in basically all the models, the first floor was the first to completely clear. And I actually did some analysis of if you include the first floor going through the exit stair versus having the first floor discharge directly to the exterior. There was a little bit of variation. It would take me more time to explain that in the slides here, but there was some impact from that. Okay. And if occupants had the opportunity to egress directly to the exterior, then the slope of this line was slightly less.
All right, and I had a comment relative to that too. I assume perhaps the longest evacuation time was always the higher floor, or was it somewhere time in the middle?
Not always.
Okay.
Not always. That seemed to be random.
Even with the SFPE mode?
Yes. It was typically a higher floor, but it was not always the highest floor.
The corollary to that is, I think you could understand a lot of this even with hand calcs or some basic flow, because, essentially you've got a choke point in these models, right? There's a controlling component. And if that flow rate can't get through, as you add more and more population by adding another floor, it's going to take everybody longer. There's going to be longer wait times. Yeah. It's obvious that that's not pushed through to the codes, but I think that, when you add another floor, if that amount of stairwell that you added can't consume that entire population for the new floor, you've just added another queue time, which makes that segment of stairway take longer to clear, which slows it down for everybody. Just commenting that it's not necessarily a model. You don't necessarily have to have a model to see it. It makes it very obvious, but I think it can be done with simple ratios too and hand calculation. Yeah. Other questions? In the back.
Hi. Did you look at varying pre-movement times in the model, or was it just everybody moving at the one time?
I'm sorry, could you repeat that first part again?
Did you look at pre-movement times, or did everybody leave at the same time?
No, this assumed simultaneous evacuation start. Yeah.
And there was a question in the front somewhere.
Thank you. Did all the agents have the same parameter set, or did you vary?
There was a distribution with the basically a Gaussian distribution of the walking speeds that are used for steering mode. For SFP mode, it was just all the standard. So using the velocity, there's a maximum velocity specified, just like in the hydraulic model, and then the model calculates that based on the density.
So you did specify only young, healthy population parameters, or did you also add some elderly, slow
Correct.
parameters?
So there was a distribution that was around basically a healthy adult as the meaning of that, but I did not manually input, let's say, a wheelchair occupant or anyone that was vastly outside of that distribution.
Okay, thank you.
Yeah.
I have a sense in this model it wouldn't have made an effect anyway because it's all controlled by a doorway at the end of every stair.
Right.
That's exactly my comment.
Right.
Okay.
We actually checked that in underground metro stations. We have a lot of queuing. It doesn't matter how you. It doesn't actually matter how you vary the input parameters. It's either if you have adults or kids or groups or
Yeah.
different distributions of speeds and pre-movement time. It is governed by the queuing.
Right.
So a lot of this parameter doesn't hold in this ones.
Right. When you have non-queued evacuation, then it's much more impactful.
Right, and it obviously controls the movement across the floors themselves. But,
Correct.
All right.
So Chris, have you developed any kind of a potentially like a function where you could put in a function of like floor level or square footage that would determine necessary egress width to try to maintain, to try to decrease the total evac time?
Right. I have not. Obviously, I do have equations for the lines you see here, best fit equations, but there's so much that goes into that that's other variables besides the number of stories. So the number of occupants on the floor geometry. Do you have a complex corridor arrangement where you're going to have a longer variation in the time for occupants from each floor to get to the stair? Or is it a wide open floor like this where everyone's just making a straight line to the stair? So I would like to, and I think that'd be very helpful to egress modelers in the future, but
I
they do some more work.
Like, how would you modify the code, right? Like if you said, okay, we need to put a code change in which says for X, Y, and Z inputs, you need so many inches per or meters per
Right.
level or whatever. So.
Right, yeah.
All right, anything else? Oh, one more.
Just one clarification and then a question. So what you're saying is the number of efficiencies goes up with the number of floors, and then that cascades back and affects the time to get off a particular floor.
Correct.
Wow, that's really cool. Okay. The other thing is, actually in Canada for NRC, we were looking to use simulation tools and flow calcs to feed back into the regulatory process, and it had a huge impact. Like they really, it was a means of an evidence-based approach to look at the consequences of regulatory change before they went into action. So I think you're absolutely right. There's an opportunity there if you can get this in front of the committees and in front of the regulators, because this is new evidence. This is a new way to test their theories before they go into practice. So yeah, I totally agree with that.
Thank you.
All right, thanks again, Chris.
Thanks.